Tonight, we're going to sit with one of the most haunting questions humanity has ever had to face. Not the question of whether we'll set foot on Mars, but the question of whether the men and women who actually do step onto that frozen, rust-stained world will ever feel Earth beneath their boots again. You've almost certainly heard the stories. The talk of Mars missions, of building cities on a foreign planet, of humanity finally claiming its place among the stars. But there's something most of those stories conveniently leave out. Something the brochures and press conferences and cinematic renderings tend to skim over. The people who reach Mars first might not be going there to explore. They might be going there to stay. Forever. And by the time we reach the end of tonight's journey together, you'll understand exactly why returning them home may be physically, financially, and philosophically impossible. Why they would still volunteer in droves, and what their decision means for the entire future of our species. Before we go any further, if the mysteries of deep space pull at you the way they pull at us, take just a moment to like this video and subscribe. It costs nothing, takes a second, and helps this channel keep finding the curious minds out there who want to explore questions like this one. Now, let's begin. Think for a moment about every single act of exploration in recorded human history. Every voyage into uncharted waters. Every expedition into territories no map had ever named. Every first ascent of a mountain previously believed unreachable. What single thread runs through all of them? The explorers came back. Magellan's surviving crew finally completed their loop around the globe and limped back into Spain in 1522. Edmund Hillary stood on the summit of Everest in 1953, then turned around and walked down. The Apollo astronauts touched the gray dust of the lunar surface, and within days were splashing into the Pacific Ocean, lifting their helmets to feel real, breathable air. No matter how brutal the danger, no matter how distant the destination, every great expedition was built around one absolute promise. You went, you discovered. You returned with the story burning in your mouth. Mars, however, may break that promise for the very first time. Mars is not the moon. Let me say that again, because the difference matters more than almost anything else in this story. Mars is not the moon. Our familiar gray companion sits roughly 400 kilometers from us. That's about 900 miles. The Apollo crews crossed that distance in roughly 3 days. From launch to splashdown, the entire mission lasted about 8 to 12 days depending on the program. From the lunar surface, the astronauts could turn their heads and see Earth itself hanging there, a small swirling marble of blue and white pinned against the blackness, close enough that you almost felt you could reach out and touch it. They were never more than a few days from their loved ones. If something failed, theoretically, help could be coordinated. The radio delay between the lunar surface and Houston was only about 1.5 seconds. Mission Control could speak to the astronauts almost as if they were across a hallway, walking them through emergencies in something that resembled real time, making decisions together, working as one connected team across the void. Mars erases all of that. On average, Mars sits about 225 million kilometers from Earth, roughly 140 million miles. But average is almost meaningless here, because both planets orbit the Sun at different speeds, sometimes drifting onto the same side of the solar system, sometimes flung onto opposite sides with the Sun blazing between them. At their closest meeting, called opposition, Mars approaches to about 55 million kilometers, around 34 million miles. At their most distant, when they sit on opposite shores of the Sun, that distance balloons to roughly 400 million kilometers, about 248 million miles. The number is constantly shifting as both worlds wheel through their separate orbital dances, and that single fact creates the very first wall any Mars mission has to climb: timing. You can't launch toward Mars on a whim. You can't decide on a Tuesday morning that next month sounds like a good time to leave. Earth and Mars must be precisely positioned in a narrow geometric arrangement before a sensible trajectory even becomes possible. That arrangement, called a launch window, opens roughly once every 26 months. Miss it, and you're staring down more than 2 years of waiting before the next one rolls around. And once you launch, the ride itself takes between 6 and 9 months, depending on the trajectory you choose. 6 to 9 months, suspended in a metal capsule, breathing the same air that's been recycled through filters thousands of times, eating the same prepackaged meals, watching the planet you were born on shrink to a pale dot in the rear window. There is no turning back, not because someone forbids it, but because the orbital mathematics simply will not allow it. The astronauts will see Earth dwindle until it joins the rest of the stars and becomes indistinguishable from them. They will become, in the truest sense, citizens of nowhere. And the conversation home? It collapses. At Mars's closest pass, a radio signal still requires about 3 minutes to reach Earth. So when an astronaut sends a question, it takes 3 minutes to arrive, and the answer takes another 3 minutes to come back, a minimum of 6 minutes for any single exchange. Once Mars drifts farther out, that delay swells to over 20 minutes one way, 40 minutes round trip, just to ask a single question and hear a single answer. Real-time conversation simply ceases to exist. You don't talk with mission control. You write to them, they write back. You wait, they wait. It becomes less like a phone call and more like a very slow, very lonely correspondence between two ships passing in opposite directions through an ocean of empty space. And if disaster strikes during those long months in transit, the crew handles it themselves. Mission Control can offer their best advice, but by the time that advice arrives, the emergency may already be settled, one way or another. But let's grant them everything. Let's say the spacecraft survives the half-year crossing without a single critical failure. The astronauts remain in good health. The life support holds. The navigation calculations prove accurate to the meter. After 6 to 9 months of empty silence and stars, Mars finally fills their windows. They fire their engines, decelerate, slip into orbit, and prepare for the most terrifying segment of the entire mission: the landing. Landing on Mars is one of the cruelest engineering puzzles in the solar system. Its atmosphere is thick enough to scorch a descending spacecraft, demanding heavy heat shields. Yet it's also too thin to slow that same spacecraft down with ordinary parachutes the way Earth would. Mars's atmosphere has only about 1% the density of our own. A parachute that would gently lower a capsule onto an Earth runway barely tugs at it on Mars. So you need retro rockets, perfectly timed, perfectly synchronized with descent radar and onboard logic. Everything must function with surgical precision. If the parachute opens a heartbeat too soon or too late, if the rockets ignite at the wrong altitude, if any single subroutine in the descent sequence misbehaves, the spacecraft becomes a smoking crater in the Martian soil. There is no second attempt. NASA engineers gave this stage a name that sticks in the throat: the 7 minutes of terror. That's how long it takes to enter the atmosphere and reach the surface. 7 full minutes during which automated systems make thousands of decisions per second, because the radio delay means no one back home can help you in the moment. By the time Mission Control sees the spacecraft beginning its descent, the lander has already been on the surface for several minutes, either resting safely or scattered in pieces across miles of red dust. The crew watches their instruments, follows procedure, and waits to see whether they're explorers or casualties. They are passengers during those 7 minutes, trusting machinery built and tested under one gravity and one atmosphere to behave correctly under another. And then, miraculously, the engines kick. The retro rockets fire on schedule. The legs touch ground. The dust settles. They have arrived. They are now standing on another world. They are the first humans in history to feel another planet under their feet. To look up at a sky no human eye has ever seen with all the layers of distance stripped away. The light is wrong. The horizon is closer than it should be. The sun looks small, distant, oddly pale. The terrain rolls out in shades of rust and copper to a line of distant mountains silhouetted against a sky that fades from butterscotch to dusty pink. It's an achievement that will be carved into the memory of our species for as long as our species exists. But there's a quiet, sobering truth waiting for them as soon as the celebration fades. They are stuck. Here's the thing nobody likes to say out loud. Getting off Mars is nearly as difficult as getting there in the first place. You need a rocket strong enough to break free of Martian gravity, accelerate to escape velocity, and aim itself back across that vast gulf toward Earth. That rocket needs fuel. An enormous quantity of fuel. Far more than anything you could realistically have brought along on the original ride. The vehicle that carried them to Mars was designed to land, not to rise again. It burned through nearly all of its propellant, slowing down, fighting the descent, kissing the surface gently. What's left in the tanks isn't even close to what's needed to climb back to orbit, so you'd need a separate machine waiting on the ground. A Mars ascent vehicle, pre-positioned, fueled, ready to ignite. Which raises an immediate question. How does that rocket get there? You have to send it ahead of the crew, land it successfully, all on its own. And then make sure it's still functional months or years later, after sitting in the open Martian environment, exposed to temperatures swinging from -125 degrees Celsius up to 20 above zero, battered by dust storms, cooked by radiation, slowly degrading the way every machine eventually does when left out in the weather. But even all of that is not the hardest part. The hardest part is the fuel. Rockets are mostly fuel. That's not a metaphor. The Saturn V, the colossal rocket that hurled Apollo astronauts toward the moon, weighed roughly 2,800 metric tons fully loaded, about 6.1 million pounds. Of that mass, around 2,600 metric tons was nothing but propellant. Only about 43 metric tons consisted of the actual command and service module that traveled to the moon and returned. That rocket was about 93% fuel by weight. And that was just to reach a world with 1/6 Earth's gravity and no atmosphere whatsoever. Mars has roughly 38% of Earth's gravitational pull. Stronger than the moon. Weaker than home. It also has that thin, dusty atmosphere that creates drag during ascent. Lifting a crew of 4 or 5 people, plus their equipment off the Martian surface and aiming them back toward Earth would require a rocket of substantial scale. And nearly all of that rocket would have to be fuel. You cannot ferry that much propellant from Earth. The mass simply won't allow it. If you tried to land a fully fueled ascent vehicle, the lander itself would be so heavy that you'd need even more fuel just to slow it down for touchdown, which adds mass, which requires more fuel, which adds more mass. The numbers spiral until they collapse on themselves. The math will not close. So here's the proposed solution that mission planners have been refining for decades. You make the fuel on Mars itself. You use what's already there. The Martian atmosphere, primarily carbon dioxide. The water ice, locked into the soil. You combine them through chemistry into methane and oxygen, the very ingredients of rocket propellant. This process has a name: in situ resource utilization. The idea is to send equipment ahead of the crew that can pull carbon dioxide from the thin air, mine water ice from the frozen ground, electrolyze that water into hydrogen and oxygen, fuse the hydrogen with the carbon dioxide through a reaction first identified by French chemist Paul Sabatier in 1897, and end up with methane and water. The water gets recycled back into more electrolysis. The methane and oxygen get liquefied and stored as the precious propellant that will, hopefully, one day blast the crew home. It's chemically possible. We've done the reactions in laboratories on Earth 1,000 times. The Martian atmosphere is conveniently 95.3% carbon dioxide, ready to be compressed and fed into reactors. Water ice exists in abundance at higher latitudes and in the permanently shadowed regions near the poles. You can heat the soil to extract it, or drill into ice deposits and capture the sublimating vapor. Once you have water, electrolysis splits each molecule into its hydrogen and oxygen components. The hydrogen then meets carbon dioxide in the Sabatier reactor. One molecule of carbon dioxide combined with 4 molecules of hydrogen becomes 1 molecule of methane and 2 molecules of water. The reaction is exothermic, meaning it releases heat that helps drive itself forward. The water created is funneled back to feed the electrolysis cycle. You only have to keep adding fresh carbon dioxide from outside. The methane and oxygen are then chilled until they liquefy. Liquid methane stays liquid at -161 degrees Celsius. Liquid oxygen demands -183 degrees Celsius. Both of those temperatures are colder than even the deepest Martian night, which means you cannot just leave them sitting in tanks. You need active refrigeration, powered cooling, insulation that minimizes the slow drip of evaporation, called boil-off, that haunts every cryogenic propellant tank. Even with the very best insulation, some fuel always escapes. If you start producing propellant a year or 2 before the crew arrives, a meaningful fraction of it can simply vanish into the Martian air before it's ever burned. And running this process in a controlled laboratory in Houston is one thing. Running it on the surface of Mars, automated, unattended, is something else entirely. You need power. Massive amounts of power, continuously, to drive the extraction units, the electrolysis stack, the chemical reactors, the liquefaction systems, the pumps, the valves, the sensors, the computers. A fuel plant capable of producing 30 to 50 metric tons of propellant over an 18 to 24-month stretch might consume 100 to 200 kilowatts of constant electrical power. That's roughly equivalent to the demand of 70 to 140 average American homes. And there is no power grid on Mars. There are no transmission lines, no substations, no neighbors to borrow electricity from. You have to bring the entire grid with you or assemble it once you arrive. Solar panels are one option. But Mars is farther from the Sun than Earth, and the math is unforgiving. At Earth's orbital distance, the Sun deposits about 1,368 watts per square meter at the top of the atmosphere. At Mars's average distance, that figure drops to around 590 watts per square meter, less than half. And that's only at local noon, on a clear day near the equator. Factor in the day-night cycle, seasonal shifts, dust suspended in the air, dust accumulating on the panels themselves, and the changing angle of the Sun across the Martian sky, and your real average power output drops sharply. You might end up needing several thousand square meters of panels to keep your fuel plant fed. Every one of those panels has to be deployed, cabled together, monitored, kept clean. And dust on Mars is a relentless daily enemy. During the dust storm season, which can stretch on for months, the atmosphere can become so heavy with suspended particles that surface sunlight drops by 50 to 99%. Global dust storms appear roughly every 3 to 4 Martian years. When one settles in, solar power can fall off a cliff. The Mars Exploration Rover Opportunity, after 15 extraordinary years of operation, finally died during a dust storm in 2018. Its solar panels could no longer feed enough power to its batteries, the heaters shut off, the rover froze, and it never woke again. A fuel production plant relying purely on sunlight could meet exactly the same fate, except this time, the consequences would not be the loss of a robotic explorer, but the stranding of a human crew. Nuclear power is far more dependable. NASA has been developing what's called the kilopower reactor, a compact fission unit roughly the size of a large trash can that can deliver about 10 kilowatts of continuous output. You'd need 10 or 20 of these to run the fuel plant, or you could use a larger reactor design, generating 100 kilowatts or more from a single core. The Soviet Union ran nuclear reactors at remote Arctic outposts for decades. The technology is real, yet launching radioactive material toward Mars introduces political and safety questions that aren't easy to wave away. What if the launch fails? What if a fragment of the core gets scattered across a launch site or spirals back into Earth's atmosphere? These risks are manageable, but not weightless. And once that reactor is on Mars, it needs cooling. You can't pour rivers of water through the system the way Earth-based reactors do, because water on Mars is precious and almost entirely frozen, so you'd use radiative cooling instead, with enormous heat radiators bleeding warmth into the Martian environment. More mass, more complexity, more moving parts that can fail at the worst possible moment. You also need automated systems clever enough to operate for months or years without anyone watching, because all of this equipment must be fueling up the propellant tanks long before the astronauts even leave Earth. Every operation has to be robotic. Sensors tracking temperature, pressure, flow rate, chemical composition, power load, structural integrity, control systems making thousands of corrections every day, opening and closing valves, starting and stopping pumps, adjusting reactor output, managing battery charge cycles, maintenance robots capable of swapping out failed components, brushing dust off solar arrays, repairing severed connectors. All of it inside a dusty, cold, radiation-soaked environment, where the nearest spare parts catalog is half a solar system away. Martian temperatures lurch wildly from one extreme to another. Near the equator on a summer day, the surface might warm to a tolerable 20 degrees Celsius. By night, it plunges to minus 73. At higher latitudes or during winter, it can collapse to minus 125 degrees Celsius or worse. Most ordinary materials become brittle at those temperatures. Seals crack. Lubricants congeal. Battery chemistries lose capacity. Electronics behave in ways the engineers never simulated. Everything, every screw, every cable, every microchip must be designed to endure thermal cycling across a 200-degree spread, day after day, year after year, without a hand to fix it. Radiation pours down constantly. Cosmic rays and solar particles slip through the thin atmosphere and hammer the surface continuously. Over time, that radiation flips bits inside computer memory, wears down solar cell efficiency, embrittles plastics and composites. A fuel plant operating autonomously for 2 years before the first astronaut arrives will have absorbed an enormous radiation dose by the time it starts seeing humans. Shielding helps, but every kilogram of shielding is a kilogram you couldn't spend on more reactors, more reagents, more habitat hardware, more science instruments. Mission planners live inside a permanent tug-of-war between protection and capability. And the plant has to actually produce tons of fuel. Literal tons. A Mars ascent vehicle might need 30 to 50 metric tons of propellant just to climb back to Mars orbit and begin the long burn home. 50 metric tons is 50,000 kilograms, about 110,000 pounds. To picture that, imagine roughly 35 automobiles, all melted down into liquid fuel. Every gram of it manufactured from local materials by equipment shipped across the void, running in one of the harshest environments anyone has ever asked machinery to survive. A well-tuned system might turn out 100 to 200 kilograms of propellant per day. At that rate, generating 50 metric tons takes 9 to 18 months of unbroken operation. Anything that breaks, any pump that seizes, any reactor that scrams offline, any dust storm that swallows the panels, halts production. The clock keeps ticking. The crew's launch window starts looming. Mission planners on Earth grow grayer by the week, refreshing data feeds from across the Gulf, hoping the equipment restarts itself, hoping enough propellant has accumulated in time. If production lags, the crew either waits longer on Mars, eating into supplies that were never designed for that duration, or risks lifting off with too little fuel, or simply doesn't lift off at all. Life support degrades. That truth never sleeps. Air recyclers gradually accumulate contaminants. Water purifiers slowly clog with mineral deposits. Spacesuit seals develop microscopic leaks. Wires fray. Filters saturate. Everything wears, no matter how carefully you babied it. Redundancy buys you time, but you can only carry so many spares. A crew that arrives expecting an 18-month surface stay and ends up trapped for 30 months because fuel production fell behind schedule will be operating well past the design margins of every system around them. Something will fail. Maybe it won't be critical. Maybe it will. Maybe they'll improvise a fix. Maybe they won't have the parts. And if propellant production halts entirely for any reason, the crew has no path home. They're stranded indefinitely. They wait for the next cargo ship from Earth to arrive bearing replacement components. Assuming Earth has the parts ready. Assuming the next launch flies on schedule. Assuming it lands intact. Years could pass before help reaches them. Meanwhile, supplies dwindle. Food and water and oxygen all stretch thinner. Rationing tightens. Hope thins along with the calories. This is the central, inescapable knot at the heart of every round-trip Mars proposal. Reaching Mars is hard. Returning is harder. And the difficulty is not merely engineering, it is logistical, and economic, and operational. And every requirement compounds against every other requirement. Every system needs backups. Every backup needs a monitor. Every conceivable failure mode needs a contingency plan that has been thought through, simulated, rehearsed. The architecture grows exponentially more complex with every additional safeguard, and complexity is the sworn enemy of reliability. The more components in your machine, the more interfaces between them, the more ways the entire structure can quietly come apart. And on Mars, the price of failure isn't a delayed launch, it's a sealed coffin in red dust. Engineers wrestle with this by building Mars simulation chambers on Earth, where they bake and freeze and irradiate and dust blast components for months on end. They build redundancy into critical systems. 2 reactors instead of 1. 3 pumps where 1 might do the job. Backup sensors, backup controllers, backup batteries. They design for graceful degradation, where the loss of one piece reduces capability without triggering catastrophic collapse. But Earth testing only goes so far. You can mimic Mars, but you cannot become Mars. The dust there is finer, more abrasive, more electrostatically clingy than any Earth analog. The atmospheric chemistry is different, the gravity is different. The radiation environment is more complex than what any Earth-based test chamber can recreate. Some lessons about Mars equipment can only be earned by actually running that equipment on Mars. And by the time those lessons arrive, the first crew may already be paying for the gap in tuition. That's why some mission planners argue for launching multiple fuel production units on separate cargo flights. If one fails, others compensate. Land them in geographically separate spots so that a single regional dust storm can't kneecap all of them at once. Begin production years ahead of the crew launch, leaving plenty of time to identify and remotely correct problems. Build a stockpile of fuel far larger than the bare minimum, so that there's margin for losses, inefficiencies, and surprises. But every additional cargo flight costs hundreds of millions of dollars. Every extra fuel plant adds mass that must be lifted from Earth and delivered to Mars. The numbers compound. A mission that might cost $50 billion with one production unit could climb to $70 or $80 billion with 3 plants running in parallel. And that money has to come from somewhere, from taxpayers, from government budgets fighting for every dollar, from private fortunes that could just as easily build something else. The honest question becomes whether society is willing to pay the price of a round trip when a one-way mission is a fraction of the cost. Think back to Apollo. The United States spent roughly $25.8 billion between 1960 and 1973 to put 12 people on the moon. Adjusted for inflation, that's about $280 billion in modern money for 12 people. For a combined total of 9 days actually walking on lunar soil, spread across 6 missions, none of which lasted more than 12.5 days from launch to splashdown. The infrastructure required was almost beyond comprehension. Hundreds of thousands of engineers, technicians, mathematicians, machinists, computer programmers all working for over a decade. New rockets had to be invented. New tracking stations were strung across islands in the Pacific and Atlantic. Every problem was first encountered. Every technology was first built. At its peak in 1966, Apollo employed over 400,000 people directly and indirectly. NASA's budget consumed more than 4% of the entire federal budget of the United States, an amount unimaginable today, when NASA receives less than half of 1%. The Saturn V remains one of the most powerful rockets ever flown to completion, and constructing it required entirely new manufacturing facilities. The Vehicle Assembly Building at Kennedy Space Center, where the Saturn V was stacked, is still one of the largest buildings by enclosed volume on the planet. The challenges in computation, navigation, and medicine were equally staggering. This was an era before modern personal computers existed, before the discipline of software engineering even had its name. Medicine in zero gravity was unknown country. New protocols had to be invented while shaving every gram of mass from every component. Life support had to be effectively perfect. 12 astronauts spent about 9 cumulative days on the lunar surface, which works out to roughly 2,000 person-hours inside the lunar module's environment, plus several thousand more inside the command module during transit. Air had to be scrubbed clean of carbon dioxide using lithium hydroxide canisters. Every drop of water had to be rationed, tracked, accounted for. Temperatures inside the spacecraft had to be held steady in a thermal environment where surfaces in sunlight reached 127 degrees Celsius, and the same surfaces in shadow plunged to -73. When Apollo 13's oxygen tank exploded, gutting the command module, the crew had to retreat into the lunar module, a vehicle designed to support 2 people for 2 days, and somehow stretch it to support 3 people for 4. They survived, just barely, through duct tape and plastic bags and improvised carbon dioxide filters, by powering down nearly every system to preserve electricity, by enduring near-freezing cabin temperatures because the heaters had to stay off. The fact that they made it home is one of the great testaments to human ingenuity in the face of disaster. And every bit of that monumental effort, every dollar, every tear, every sleepless month, was expended on missions to a body 3 days away. A world with no atmosphere to wrestle during landing. A world with 1/6 Earth's gravity, where lifting off again was relatively gentle. A world where the communication delay was measured in seconds, not in tens of minutes. A world where Earth was always visible in the sky, hanging there like a blue reassurance. If you suffered a medical crisis on the moon, you could be back in Earth orbit within 3 days, and inside a hospital within 4. Tight, but survivable. If a critical system failed, you could simply abort the mission and run for home. Apollo 13 proved exactly that. A round-trip Mars mission would cost exponentially more. The spacecraft would need to be larger to accommodate the longer journey. You would need more supplies, more redundancy, more life support throughput. Instead of a 1-week mission, you're staring down a 3-year campaign. Instead of 3 astronauts crammed into a capsule the size of a van, you'd need 6 to 8 astronauts inside a habitat large enough that they don't psychologically destroy each other. Instead of consumables stored in tanks, you'd need regenerative life support that recycles air and water across years. Instead of batteries and fuel cells, you'd need nuclear reactors or huge solar farms. Instead of 1 lunar module, you'd need descent vehicles, surface habitats, rovers, ascent vehicles, fuel production plants, and every layer of infrastructure required to support all of them. The mass numbers are staggering. The combined Apollo Command and Service Module weighed about 32 metric tons. A Mars transit vehicle could weigh several hundred metric tons fully loaded. The lunar module weighed about 15 metric tons. A Mars lander with habitat could weigh 100 metric tons or more. Everything scales upward. More mass demands more launch fuel. More launch fuel demands larger rockets. Larger rockets demand more development. The costs compound at every step. And then you also need the ascent vehicle, the fuel production infrastructure on Mars itself, and all the systems to keep the crew alive during the 1.5 years they'll be sitting on the surface waiting for the next launch window to swing open, because you cannot leave whenever the crew feels homesick. Just as the trip to Mars demands a planetary alignment, the trip back demands the same. If you arrive on Mars and the optimal return window has just slipped by, you're stuck waiting roughly 26 months for the next one. There is no shortcut. Orbital mechanics is a stone wall that does not negotiate. 2 years on Mars. 730 days, minimum. That's how long the crew would have to survive inside their habitat. Breathing recycled air. Drinking water that has been through the system more times than they care to count. Eating stored rations supplemented by whatever they can coax out of pressurized greenhouses. The psychological challenge of that duration is hard to overstate. You're sealed inside a few rooms, or if you're lucky, a few connected modules. You can step outside, but only inside a stiff, hot, exhausting spacesuit. You can never feel wind on your face. Never smell rain on warm Earth. Never see green leaves swaying. Never take a casual walk. Everything you sense through a visor, a glove, a microphone. Research on long-duration confinement, from Antarctic stations to submarines to the International Space Station, shows that crews experience meaningful psychological strain after about 6 months. Small habits begin to grate, depression creeps in, sleep patterns break down, cognitive performance dips, slowly, like a tide going out. These effects build gradually, almost invisibly, until one day someone realizes they aren't operating at full capacity anymore. Physical health bleeds away too. Mars' gravity is only 38% of Earth's. Bones don't have to support as much weight. Muscles don't have to fight as hard. Even with rigorous daily exercise, bone density still falls, and muscles still atrophy. Astronauts on the International Space Station, in zero gravity, lose about 1 to 2% of their bone mass per month, despite spending 2 hours a day exercising. On Mars, with partial gravity, that loss would be slower, but still relentless. After 2 years, an astronaut could have shed 20 to 30% of their bone density, raising their fracture risk and potentially condemning them to chronic pain. Medical issues are another constant fear humming behind every shift. What happens if someone develops appendicitis? On Earth, that's a routine surgical case, almost forgotten the moment it's done. On Mars, with no full hospital, no surgical suite, no anesthesiologist, no blood bank, it becomes a possible death sentence. You could train 1 crew member as a physician, equip them with surgical kits and medical supplies. But one person, however gifted, isn't a surgical team. Complex operations require multiple specialists working in unison. A surgeon, an anesthesiologist, a radiologist, a surgical nurse, a dentist. You can't fit all those specialties into a 6-person crew, while also covering engineering, geology, biology, chemistry, agriculture, piloting, and every other discipline the mission demands. Telemedicine helps. The doctor on Mars could video conference with specialists on Earth, drawing on their experience during a procedure. But remember the communication delay. 20 minutes one way. When Mars is far from Earth, you cannot have a specialist guiding you stitch by stitch. Their advice arrives 10 minutes after you needed it. The Martian doctor would essentially be alone, leaning on pre-recorded training videos, written procedures, and the strength of their own judgment under fire. Radiation exposure piles up relentlessly during those 2 surface years. Cosmic rays slip through the thin atmosphere and arrive almost unfiltered. A year on the Martian surface exposes you to roughly 240 millisieverts of radiation, compared to about 3 millisieverts per year on Earth. The increased cancer risk is significant, though not immediately fatal. It's the kind of damage that simmers, perhaps invisibly, for decades. But it is cumulative. Every day on Mars adds to a lifetime dose. Every hour spent outside in a spacesuit, where shielding is minimal, adds even more. By the time the crew steps back into Earth's atmosphere, if they ever do, they'll have absorbed radiation totals that current NASA safety standards would never permit for any existing mission. Those standards exist because the data is unambiguous. Studies of atomic bomb survivors, of radiation therapy patients, of nuclear accident workers, of long-duration astronauts, all show clean correlations between radiation dose and cancer rates. More radiation means higher cancer risk. For a Mars mission, planners would have to publicly accept higher risks than any human spaceflight program in history has ever tolerated. Some argue the crew can make that decision themselves with full informed consent. Others argue it is unethical to expose anyone to that much radiation at all, regardless of consent. And all of this assumes a certain baseline of luck. No major equipment failures. No unexpected medical emergencies. No psychological collapses. No accidents during a surface excursion. But Murphy's Law applies on Mars exactly as it does on Earth. Anything that can go wrong eventually will, given enough time. And 2 years is a great deal of time. The habitat could develop a leak. Micrometeorites, tiny grains traveling at extreme velocities, hammer the Martian surface continuously because the atmosphere is too thin to vaporize them the way Earth's does. A single micrometeorite impact could puncture a habitat wall. If the hole is small, a few millimeters across, the air loss might be slow enough to detect and patch before pressure drops dangerously. If it's larger, the habitat could depressurize within minutes. The crew would have to seal themselves into spacesuits, find the breach, patch it from the outside if necessary, all while managing the cold panic of a possibly fatal emergency. Or a critical system could quietly fail. The oxygen generator stops, the water recycler clogs, the carbon dioxide scrubbers saturate. Each of these failures is a slow countdown. Without oxygen, you have minutes. Without water, days. Without carbon dioxide removal, hours to days, depending on cabin volume and crew size. Redundancy buys time but adds mass and cost, and even redundant systems can fail simultaneously. The crew would have to be exceptionally resourceful. They'd diagnose problems with limited tools, repair equipment with whatever materials happen to be on hand, improvise solutions that no one ever wrote into a manual. They'd think creatively under pressure. They'd hold their composure when lives hung on the next decision. These are the same qualities that saved Apollo 13. Improvisation, determination, the capacity to solve impossible problems with insufficient resources. But Apollo 13 lasted less than a week. A Mars mission demands that level of performance, day after day, month after month, year after year. And throughout it all, the crew is also accumulating bone loss, muscle atrophy, radiation, isolation, and the constant background awareness that any rescue is at minimum 6 to 9 months away. If something goes catastrophically wrong, if the habitat is destroyed, if multiple crew members die, if a solar flare floods the area with lethal radiation, no rescue mission is coming. Earth can send condolences, maybe a memorial expedition years later, But no one can save anyone in real time. The crew is more alone than any human explorers have ever been. After those 2 long years, if everything is held together, if the fuel is stockpiled, if the ascent vehicle is functional, the crew climbs aboard, ignites their engines, lifts off the Martian surface, and begins another 6 to 9 month journey home. Another half year inside a metal cabin. Another long stretch of fingers crossed. The full mission from Earth orbit departure to splashdown would consume about 3 years, 36 months of one continuous mission. And when they finally step back onto their home planet, if they do, they face months of rehabilitation. Their bones are weakened, their muscles are atrophied, their cardiovascular systems have settled into Mars-level demand and have to be retrained for full Earth gravity. They'll need physical therapy, maybe surgery, definitely lifelong medical monitoring for radiation-induced cancers. The first Mars crew would be patients as much as heroes, walking case studies of what multi-year deep space missions do to human bodies. Is it worth it? That's a values question, in the end. What is it worth to put a handful of people on Mars, let them stay for 2 years, and bring them back? What scientific knowledge would we gain that robots can't already gather? What does it really mean, in concrete terms, to plant a flag and leave footprints? What inspiration might it offer to future generations? The scientific case is genuinely weak. Robots can do most of what humans can on Mars, and they do it without life support, without rations, without the need to come home, without anyone risking their life. Rovers like Perseverance and Curiosity have operated for years, analyzing rocks, drilling cores, scanning for biosignatures, sending data back. They don't get tired. They don't need food or water or psychological counseling. They don't fear radiation. You can send 10 robots for the cost of 1 human mission. And if a robot dies, it's regrettable, but not tragic. No one is buried in the dust. Humans do have advantages, of course: flexibility, adaptability, the ability to make complex judgments in real time, the capacity for creative problem-solving that no autonomous system has yet matched. A geologist standing on Mars could spot an unusual formation, decide on the spot to investigate, modify their sampling strategy in minutes. A robot needs detailed instructions transmitted from Earth, and by the time those instructions arrive and execute, the moment may have passed. Humans can also perform repairs and improvisations far beyond the reach of current robotics. But are those advantages worth hundreds of billions of dollars and the very real chance of crew death? The argument continues. Some say exploration is fundamental to who we are, that the impulse to push outward is hard-coded, that we should go to Mars for the same reason we climbed Everest or sailed for Antarctica, because it is there, because we can, because not going feels like betraying something essential about being human. Others call that romanticism, not policy. They argue that space budgets are finite, that money spent on a single human Mars mission could fund dozens of robotic missions across Mars, the moons of Jupiter and Saturn, asteroids, comets, and telescopes hunting for Earth-like planets around distant stars, that the scientific yield per dollar is far higher with robots, that flags and footprints aren't worth lives or vast sums that could be solving problems here at home. And then there's the third option that quietly rewrites every equation. What if they don't come back? A one-way Mars mission completely transforms the calculus. Suddenly, you don't need an ascent vehicle. You don't need a fuel production plant pre-deployed on the surface. You don't need to wait 26 months for a return launch window. You don't need to provision for another 6 to 9 months of return trip life support. The mission becomes simpler, cheaper, and, in some ways, ironically safer. You send the crew, you land them, you set them up with a permanent habitat, they live there. They become the first Martians. They establish a presence that doesn't end when their souvenir bags are full. But one way is not just a technical change to a mission profile. It is a fundamental rewrite of what you are asking people to do. You aren't asking them to take a 3-year trip to Mars and back. You are asking them to leave Earth forever, to accept that they will never again walk on a beach, never swim in an ocean, never hike through a forest, never feel a summer thunderstorm break across a hot afternoon, never smell flowers, never attend a wedding or a birthday or a funeral on the planet they were born on, never visit their hometown. Every goodbye is the final goodbye. Every last glance at Earth from the spacecraft window really is the last. There are no second thoughts, no turning around, no coming home for emergencies. This is not a brand new idea. Mars One, a private organization founded by Bos Lansdorp in the Netherlands, proposed exactly this concept in 2012. They planned to send volunteers on a one-way trip to Mars to establish a permanent colony, resupplied periodically, but never bringing anyone back. The plan was ambitious, perhaps recklessly so. The funding was supposed to come from reality television, broadcasting the selection process, the training, the launch, the landing, the daily life on Mars, all as global entertainment, with hundreds of millions of viewers tuning in to watch ordinary people become Martians. The advertising revenue would supposedly underwrite future missions. The response stunned everyone. Mars One received over 200,000 applications from people in more than 140 countries: teachers, engineers, students, doctors, veterans, artists, people from every conceivable profession and age range. Some had advanced degrees and seemed perfectly qualified on paper. Others had no relevant credentials at all, but were willing to spend years learning. What they shared was a willingness to leave everything behind for a chance to be part of something historic. The project ultimately collapsed. Money ran short. The technical challenges proved more brutal than anticipated. Critics raised serious questions about whether Mars One had the engineering depth to actually deliver. By 2019, the company had filed for bankruptcy. They'd produced promotional materials, generated worldwide press, and built no hardware. They had not secured launch contracts. They had not developed the technologies necessary to keep humans alive on Mars indefinitely. But the fact that 200,000 people applied tells us something profound about human nature. People are willing to take enormous risks, to make incredible sacrifices, for causes they believe in, for the chance to be part of something historic, for the rare opportunity to truly matter in a way that ordinary life almost never offers. The psychological screening for a real one-way mission would be ferocious. The training would consume years. The risks would be communicated bluntly, in plain language. Applicants would be told, repeatedly and unambiguously, that they are choosing to spend the rest of their lives on Mars, that there will be no rescue, no evacuation, no turning back once they launch. And yet, thousands of qualified people would still apply. We know this because human history has always written itself in this same handwriting. The Pilgrims who crossed the Atlantic on the Mayflower in 1620 understood that they were almost certainly never returning to England. The mortality rate of those early settlements was horrific. Yet people kept coming, drawn by religious freedom, by economic opportunity, by the simple, stubborn desire for a fresh start in a new place. The pioneers who walked the Oregon Trail through the 1800s endured months in hostile country, watching loved ones die of disease, exposure, and accident. Many never reached the coast, yet thousands followed the same paths. Ernest Shackleton, planning his Antarctic expedition in 1914, supposedly placed an advertisement that has become legend. Men wanted for hazardous journey. Small wages, bitter cold. Long months of complete darkness. Constant danger. Safe return, doubtful. Honor and recognition in case of success. He received over 5,000 applications for 28 positions. They knew the risks, they went anyway. The first Mars colonists would belong to that same tradition. They would be pioneers, not tourists. They would understand they were trading their old lives for a new existence on another world. They would know the risks, they would accept them. They'd train for years, possibly 5 to 10 of them, depending on the candidates. Starting backgrounds. They'd master an enormous catalog of skills, basic medicine, from setting broken bones to performing emergency surgery. Engineering deep enough to repair almost any system in the habitat. Agricultural science for coaxing food out of pressurized greenhouses. Geology for choosing samples and conducting field research. Piloting for rovers and drones. Construction techniques for expanding the habitat using local materials. They'd train in Mars analog environments, remote spots on Earth that imitate aspects of the Martian surface. The Mars Desert Research Station in Utah. The Flashline Mars Arctic Research Station in the Canadian Arctic. The volcanic regions of Iceland. The high deserts of Chile. They'd spend months at a time inside simulated habitats, going outside only in simulated suits, eating simulated Mars rations, dealing with simulated equipment failures. None of it perfectly captures Mars, of course. No place on Earth combines thin atmosphere, low gravity, extreme cold, and harsh radiation the way Mars does. But it gets them as close as a planet of trees and oceans can. Psychological preparation would be just as rigorous. Psychiatric evaluations would screen for candidates predisposed to depression, anxiety, or other conditions that could become catastrophic in the Martian environment. Selectors would search for emotional stability, stress tolerance, the kind of resilience that doesn't crack under exhaustion or fear. They'd look for interpersonal skills that allow someone to resolve conflicts without letting them rot into permanent grudges. Group dynamics would be analyzed obsessively. 6 to 8 people sharing a small habitat for years need to be deeply compatible. They need to respect each other, to work together, to support each other through hard moments. One toxic personality could poison everyone. Studies of Antarctic stations, submarines, and the International Space Station have shown that interpersonal friction is one of the largest stressors in any isolated environment. Tiny irritations grow into mountain ranges over months. The way someone chews, their hygiene habits, their sense of humor, their work style. Any of these can become a flashpoint when there is no escape. The crew would need shared purpose, something binding them together and giving meaning to their sacrifice. This is one of the reasons early Earth colonists often had strong religious or ideological convictions. Their faith framed hardship as meaningful, not pointless. Modern Mars colonists might not be religious, but they would need something analogous. A deep, durable belief in the importance of establishing humanity on another world. A conviction that they're contributing to the long-term survival of their species. A sense that their sacrifice carves a path future generations can walk. Psychological support would continue throughout training and through every day on Mars. Regular counseling sessions. Group therapy. Vigilant monitoring for any drift toward mental health collapse. On Mars, they'd have access to telecounseling with therapists on Earth. But the communication delay limits its usefulness. You cannot have a real-time therapy session when each exchange takes 20 to 40 minutes round trip. Instead, the crew would send updates. The therapist would review them and respond hours later with reflections and advice. The colonist would absorb that response over coffee made from twice recycled water. Better than nothing. Not the same as a quiet office and a kind voice in person. The mission would likely begin small, with 4 to 6 people in the first crew. Their habitat would already be on the ground when they arrived, having been delivered by automated cargo flights months or years earlier and tested thoroughly. Solar panels would already be deployed, airlocks already cycled, life support already proven. The crew's spacecraft would land near the habitat, close enough to walk over in an hour or two wearing suits, but not so close that landing debris could damage anything important. The first weeks would be brutal, unloading equipment, moving it inside, setting up redundant systems, testing everything obsessively, establishing routines for daily life, for maintenance, for scientific work, beginning the slow psychological adjustment to a new reality. The novelty would carry them through the first stretch. Everything is new. Everything is exciting. They are on Mars. They are making history. They are the first humans to live on another planet. But after a few months, reality settles in. This is life now. The same habitat every day. The same few rooms. The same faces. The same food. The same rhythms. Mars itself does not change. The landscape today looks almost identical to yesterday, and will look almost identical tomorrow. The sky is always that pale, dusty pink. The sun is always small and distant. The rocks are always rust-colored. There are no seasons in the way Earth has seasons. Just gradual shifts in temperature as Mars wheels around the sun on its long, slow orbit. They'd have work to keep them grounded. Scientific research is the primary justification for their presence. They'd run geological surveys, collect samples, hunt for traces of ancient life, study Martian weather patterns, test technologies meant for future colonists. They'd set up instruments, maintain equipment, Document findings. Send data home. Scientists on Earth would analyze the results, send back questions and follow-up requests. Collaborate across the Gulf as best as the delay allows. Agriculture would consume an enormous share of their time and attention. Growing food on Mars is essential for any kind of long-term self-sufficiency. Greenhouses would be pressurized with a mixture of nitrogen and oxygen, warmed to comfortable temperatures, illuminated by LED arrays tuned precisely to the wavelengths plants love most. The colonists would grow fast crops first: lettuce, spinach, radishes, tomatoes. Possibly potatoes, which can deliver substantial calories even in poor soil. Maybe eventually rice or wheat, although grains take longer and yield less per square meter than vegetables. The soil would be Martian regolith, processed to remove toxic perchlorates and supplemented with organic matter from human waste. Composting toilets would recycle biological material, although the process requires careful management to keep pathogens from becoming a threat. Water would come from melted ice, purified and recycled through the life support system. Nutrients would arrive from Earth at first, but the colony's long-term goal would be to derive everything possible from Martian resources. A crop failure would be devastating. If a disease wiped out a greenhouse, if a seal failed and crops froze, if lighting systems malfunctioned and plants didn't get enough light, the colony would face the very real possibility of starvation. They'd have emergency food supplies, freeze-dried rations, preserved goods sent from Earth. But those are finite. If multiple crop cycles failed, they'd have to ration severely, waiting for the next resupply mission to arrive and praying it lands on schedule. Maintenance would be constant, endless. Spacesuits develop leaks and tears. Air recyclers clog with dust. Water purifiers accumulate mineral deposits. Solar panels need brushing. Batteries degrade. Every system has a finite lifespan and eventually fails. The colonists would need workshops, tools, spare parts, and raw materials for fabricating replacements. They'd need the knowledge and ingenuity to keep equipment running far longer than its original design called for. This is precisely where human presence pays for itself in ways robots cannot match. A human engineer can stare at a broken pump, intuit what failed, and figure out a workaround using scavenged materials. They can repurpose components from one system to repair another. They can improvise solutions that no engineer back home would ever think of. The Apollo 13 crew survived through exactly this kind of improvisation. Mars colonists would need that skill set, but sustained over years rather than days. Social structure would evolve organically. In a crew of 6, there is no room for rigid hierarchy. Everyone needs to contribute. Everyone's skills matter. Everyone's voice matters. Decision-making would probably lean consensus-based, with the crew talking through issues and reaching shared agreement, rather than a commander barking orders. In genuine emergencies, someone has to make rapid calls, so they would likely designate a mission commander with crisis authority. But for daily operations, collaborative decision-making builds buy-in and supports morale. Celebrations and rituals would become disproportionately important. Marking time becomes a survival skill in places where time risks dissolving into a single endless day. Birthdays. Anniversaries of landing. Holidays adapted from each colonist's culture. They might invent new Martian holidays of their own, commemorating significant moments in the colony's history. The first successful greenhouse harvest. The first child born on Mars, if the colony grows large enough. The first time a colonist sets foot in a new region, expanding the human map of another world. Conflict would be inevitable. Pack 6 people into a confined volume for years and you will get on each other's nerves. Disagreements about how to prioritize tasks. About who is doing their fair share of the maintenance. About how to allocate scarce resources. About whether scientific objectives or survival should come first when they collide. Small resentments fester when there is no door to walk out of. Someone who doesn't clean up after themselves in the communal kitchen. Someone who makes too much noise during sleep periods. Someone who hogs the limited bandwidth used for communication with Earth. The crew would need real conflict resolution skills. The ability to address issues directly but respectfully. To express frustration without attacking personalities. To forgive minor infractions instead of cataloging them. To compromise when perfect agreement is impossible. They would probably hold regular group meetings where everyone could air grievances and work through tension before it metastasized. Physical intimacy is a complicated topic that mission planners cannot pretend doesn't exist. Will romantic relationships form? Almost certainly, if the crew is mixed gender. You cannot simply suppress human attraction through training or screening. People will form emotional bonds, including romantic ones. The question is how to handle that without breeding jealousy, favoritism, or relationship drama that contaminates the entire crew. Some planners suggest sending established couples, people who've already weathered years together. Others argue that even strong relationships often crack under the unique pressure of a Mars mission, and a breakup inside a sealed habitat could be devastating to morale. Pregnancy would be a disaster for the earliest missions. Not because children on Mars are inherently a problem, but because the first colonists are not equipped for childbirth or child-rearing. They don't have obstetricians, they don't have pediatricians, they don't have neonatal intensive care units. Pregnancy in low gravity under elevated radiation carries unknown risks. Fetal development might unfold differently. Birth might be complicated by factors that are trivial on Earth and lethal on Mars. Even if a birth went well, caring for an infant inside a pressurized habitat while also conducting research and maintaining life support would stretch the crew beyond capacity. Later missions, once the colony has grown larger and more capable, might include families. Children would grow up on Mars knowing it as home. They'd encounter Earth only through images and stories. They'd look up at Earth in the night sky, sometimes bright enough to cast faint shadows when it sits at closest approach, and try to imagine oceans and forests and billions of people, but it would all be abstract. Mars would be real, the rust-colored dirt under their feet, the thin, cold air just beyond the airlock, the familiar daily rhythms of life inside a pressurized dome. Those children might never be able to visit Earth. Their bones and muscles would have developed under 38% gravity, and stepping onto Earth's full pull would feel as if they had suddenly tripled in weight. Their hearts would struggle. Their joints would ache. They'd be Martians in every meaningful sense, beautifully adapted to their world, biologically incompatible with the planet where their species first evolved. But they wouldn't care. Earth would be the alien world. Mars would be normal. They'd grow up learning Martian geology, Martian geography, Martian history. The story of the first colonists who came from Earth and stayed. The early struggles to establish habitats. The slow expansion as more missions arrived. The gradual emergence of a Martian culture, distinct from Earth culture, but still drawing on it. Culture would evolve in directions no one can fully predict. Language might shift. New words for Martian phenomena that have no Earth equivalent. Slang born from the colonist experience. Possibly even subtle grammatical drifts over generations as Martian children absorb Earth languages reshaped by their parents' new contexts. Art would reflect the Martian environment. Paintings and photographs of rust deserts and pink skies. Music composed inside the strange acoustic landscape of a thin atmosphere where sound travels differently. Literature exploring the themes of isolation, sacrifice, and the long, patient labor of building something new from nothing. Political structure would eventually become unavoidable. The first crew operates under authority delegated from whatever organization sent them, NASA or SpaceX or a coalition of agencies. But as the colony grows, as second and third generation Martians are born, governance questions become impossible to ignore. Who makes decisions? Who enforces rules? How are disputes resolved? Do colonists have legal rights? Do they owe political allegiance to Earth governments? Are they autonomous? These questions might feel premature today, but history shows that colonies eventually push toward independence. The American colonies declared independence from Britain. Australia evolved from a penal colony into an autonomous nation. Even Antarctica, governed by international treaty, has ongoing debates about sovereignty and resource rights. Mars would walk a similar path, only accelerated, because the physical separation is so much greater. Earth cannot send military forces to Mars. The journey takes too long. The cost is too astronomical. The cooperation required is too fragile. By the time a punitive expedition arrived, the political situation on Mars would have changed completely. A Martian declaration of independence might come decades or centuries after the first landing. Or it might come almost immediately. If the first colonists felt that Earth was making unreasonable demands or treating them as expendable assets, Imagine a scenario in which Earth Mission Control orders the colonists to risk their lives for a scientific objective that seems pointless to the people actually living on Mars. Do they obey, accepting Earth's authority? Or do they refuse, asserting their right to make decisions about their own safety? The communication delay quietly tilts the balance of power. Earth can issue orders, but Mars has 20 to 40 minutes before Earth even learns how Mars responded. Actions can be completed before objections can register. This communication asymmetry fundamentally rewrites who actually holds authority in any conflict. Commands become harder to enforce when they arrive minutes or hours after the moment they were needed. Economic relationships would be tangled. The first missions are funded by Earth governments or private organizations expecting some return. That return might be scientific data, media rights, prestige, or strategic positioning for future resource extraction. But what happens when Mars becomes self-sufficient? When colonists grow their own food, manufacture their own tools, no longer depend on Earth for basic survival? The economic justification for continued funding becomes murky. Mars has resources Earth might want: water ice in vast quantities, minerals, possibly including rare earth elements, deuterium, a hydrogen isotope useful for fusion reactors if fusion power ever becomes viable, carbon dioxide for industrial chemistry. Iron oxide, the rust that gives Mars its color, could be processed for iron and oxygen. But extracting these resources and shipping them back to Earth requires staggering infrastructure and energy. It would almost certainly be cheaper to mine the same materials from asteroids or the Moon, both of which sit closer and at lower gravities, making launches easier. The real value of Mars might be strategic rather than economic. A second home for human civilization. Insurance against Earth-focused catastrophes. A staging point for exploring the outer solar system, closer to the asteroid belt and the moons of Jupiter and Saturn than Earth is. A research station for studying planetary formation, astrobiology, and the long-term effects of low gravity and high radiation on human bodies. None of these generate profit in the conventional sense, but they generate value that justifies continued investment. Over time, the colony would become more self-reliant, depending less on Earth for survival. Each cargo mission delivers equipment that enables greater independence. 3D printers that can fabricate tools and spare parts. Industrial equipment for refining Martian ores into pure metals. Chemical plants for producing plastics, fertilizers, pharmaceuticals. Genetic libraries for agricultural diversity. Educational materials for teaching Martian-born children. Each increment of independence makes the colony more resilient, less vulnerable to a delayed or canceled supply ship. Eventually, perhaps a century or two after the first landing, Mars might host tens of thousands of inhabitants, cities buried underground or sheltered inside pressurized domes, farms producing most of the food, factories building most of the equipment, universities researching Martian-specific challenges, spaceports launching missions further outward to the asteroid belt and beyond. At that point, Mars would be truly independent, a second branch of human civilization pursuing its own destiny while still trading information and culture with Earth. Now, think about the mass savings on a one-way mission. A spacecraft built for a one-way trip doesn't need to carry fuel for the return journey. It doesn't need to carry an ascent vehicle. It doesn't need to provide as much life support for those extra months in space. Every kilogram you save can be redirected to something else. More supplies for the surface stay, more equipment for the habitat, more redundancy in critical systems, more scientific instruments, more of everything that keeps people alive and engaged on Mars. Costs collapse dramatically. Instead of hundreds of billions of dollars or a full trillion, a one-way mission might cost in the tens of billions. Still expensive. Still a massive undertaking. But within reach of a single wealthy nation or a coalition of nations, you could potentially launch a one-way Mars mission within the next 10 to 20 years using existing technology and some focused development. It wouldn't require revolutionary breakthroughs. It would require commitment and funding. But would anyone actually go? Would real human beings volunteer for a one-way trip to Mars knowing they would never see Earth again? Never breathe unfiltered air. Never feel rain on their face. Never swim in an ocean. Never walk through a forest. Would they accept a life confined to a few pressurized habitats and bulky spacesuits? Living on a cold, dead world with a toxic atmosphere completely dependent on technology for every breath, every drop of water, every calorie of food? The answer is yes. People absolutely would volunteer. We've already seen it. When Mars One announced their mission, they received over 200,000 applications from people in more than 140 countries. 200,000 people willing to leave Earth forever for a chance to be part of history, to set foot on another planet, to become Martians. The screening would be unforgiving. The training would consume years. The risks would be communicated transparently. And yet thousands of qualified people would still apply. Why? Because exploration is built into the human story. Because some people genuinely value discovery more than comfort. Because the chance to be part of something larger than yourself, to contribute to humanity's future, to be remembered for generations, speaks to certain personalities in ways that safety and familiarity never could. The people who crossed the Atlantic to settle the Americas in the 1600s knew they were probably never coming home. The journey was dangerous. The destination was unknown. The life would be hard. Many didn't survive, but they went anyway, propelled by hope, ambition, and the gravitational pull of the unfamiliar. The first Mars colonists would walk that same lineage. They would be pioneers, not tourists. They would understand they were trading their old lives for a new existence on another world. They would know the risks. They would accept them. They would train for years, say goodbye to family and friends, and board the spacecraft, knowing they were leaving Earth forever. And here is the thing. Once they're on Mars, they wouldn't need rescue, they would need supplies. Yes. Regular cargo missions, delivering food, spare parts, medical kits, new equipment. But they wouldn't need to be evacuated. They'd adapt. They would make Mars their home. They would learn to live in that environment, to work in that environment, to thrive in that environment. Over time, the colony would become more self-sufficient, growing more of its own food, manufacturing more of its own tools, depending less on Earth for the basics of survival. Eventually, years or decades down the line, a Mars colony could even develop the capability to manufacture a return vehicle. They'd have the industrial base, the fuel production lines, the expertise. Someone born on Mars, someone who'd never seen Earth except as a bright star in the sky, might one day decide they wanted to visit the home world of their species. And by then, the technology and resources would exist to make that possible. But that comes later, after the colony is built, after the infrastructure is mature, after Mars has become, in every meaningful sense, a second home for humanity. The first humans on Mars almost certainly will not come back, because bringing them back is not the goal. The goal is to establish a permanent human presence on another world, to ensure that humanity is not confined to a single planet vulnerable to whatever catastrophes may eventually befall Earth. An asteroid impact, supervolcano eruption, a pandemic, a nuclear war, a runaway climate catastrophe. Any of these could devastate Earth's biosphere and threaten human civilization at its root. But if there are people on Mars, if there are self-sustaining colonies on multiple worlds, then humanity as a species survives. We become an interplanetary civilization, spread across the solar system, no longer betting everything on a single planet. This is the real reason for going to Mars and staying there. Not because it is easy or cheap or safe, because it is necessary for our long-term survival. Because keeping all of humanity's eggs in one basket, no matter how blue and beautiful and life-supporting that basket may be, is a risk we should not accept if we have the technology to do something about it. Mars is the obvious first choice for a colony. It is the closest planet with a solid surface that isn't a hellish furnace like Venus. It has water ice that can be extracted and purified. It has an atmosphere, thin as it is, that can be processed for oxygen and other useful gases. It has a day length 24 hours and 39 minutes, close enough to Earth's that humans can adapt their circadian rhythms without too much difficulty. It has seasons caused by its axial tilt, although they last about twice as long as Earth's seasons, because Mars takes longer to orbit the Sun. It has temperatures that, while frigid by Earth standards, are survivable with proper insulation and heating. the average surface temperature is minus 63 degrees Celsius. But near the equator in summer, daytime temperatures can climb to a comfortable 20 degrees Celsius before plunging again at night. The low gravity is a challenge. At 38% of Earth's pull, long-term residents would experience bone density loss and muscle atrophy. Children born on Mars might develop differently than children on Earth, with weaker bones and muscles tuned to lower gravity. They might never be able to visit Earth because they could not withstand the higher pull. But they wouldn't care. Mars would be their home. Earth would be the alien world, the place with crushingly heavy gravity where everything weighs nearly 3 times as much. The radiation is a serious concern. Mars has no global magnetic field and only a thin atmosphere, so cosmic rays and solar particles reach the surface with minimal shielding. Long-term exposure raises cancer risk and could create other health problems. Colonists would need habitats with serious radiation shielding, possibly built underground or piled over with Martian regolith. They'd limit time spent outside in spacesuits. They'd undergo medical monitoring and treatments tuned to chronic exposure. But these are solvable problems. We know how to shield against radiation. We know how to monitor exposure. It's an engineering challenge, not an impassable barrier. The psychological challenges might prove harder than the physical ones. Humans evolved for life on Earth, for blue skies and green plants, and the sounds of wind and water and animals. Mars has none of that. The sky is butterscotch pink during the day, fading to a strange blue near the sun at sunset, in a haunting reversal of Earth's colors. There are no plants outside of greenhouses, no animals, no insects, no birds, no sound except what humans and their machines make. The landscape has its own stark beauty: vast rust-colored deserts, towering volcanoes, canyons deep enough to swallow Everest. But it is empty, lifeless, alien. The colonists would have to create their own culture, their own community, their own reasons for being that go beyond mere survival. They would need art and music and literature, games and celebrations and rituals, connection to each other and to their mission. They would need to build a community capable of sustaining itself psychologically as much as physically. This may be the hardest part of the entire endeavor. Not the technology, not the logistics, the human element. Keeping people sane and motivated and engaged across years and decades inside an environment that is fundamentally hostile to human life. But here is what gives me hope. Humans are extraordinarily adaptable. We've colonized every environment on Earth, from the Arctic to the Sahara, from high mountain valleys to tropical archipelagos. We have lived continuously aboard the International Space Station since the year 2000, maintaining a human presence in space for over 2 decades. We have learned how to thrive in places that would kill us within minutes if we removed our technology. Mars would be the ultimate test of that adaptability. But it is not beyond our capabilities. The first Mars colonists would be heroes. They would be remembered for as long as human civilization endures. Their names would be taught to children on both Earth and Mars. They'd be the Neil Armstrong and Buzz Aldrin of the next generation. The people who took the first real steps toward making humanity a multiplanetary species. But unlike Armstrong and Aldrin, who walked on the moon for a few hours and came home, the Mars colonists would live there. They would live out their entire lives there. Their bodies would eventually be committed to Martian soil, becoming, atom by atom, part of another world. And there is something quietly beautiful about that. Humans evolved on Earth, but we are capable of becoming something more. We are capable of adapting to new worlds, of building homes in places no human has ever lived. The first people to die on Mars would be the first humans whose atoms would never return to Earth. They would become part of Mars forever. Their sacrifice would make every future generation of Martians possible. Their decision to go and never return would open the door for millions, eventually billions of people to follow, to build cities and farms and schools, to gradually terraform the planet over centuries, to turn Mars into a true second Earth. Because that is the long-term vision, not a small outpost of a few dozen people clinging to survival, but a thriving civilization of millions of inhabitants. Cities under domes or carved into lava tubes, connected by tunnels and transit systems. Farms producing food. factories manufacturing goods, universities researching new technologies, a government, a culture, an economy. A world that is unmistakably Martian while still carrying its Earth heritage like a quiet thread woven into every part of life. Getting there would take centuries. The first colonists would only see the very beginning. They would live in small habitats, probably underground or inside lava tubes for radiation protection. They would work constantly to maintain their life support, to grow food, to conduct research that justifies the staggering expense of supplying them from Earth. They would know they were building a foundation for something they would never see completed. They were planting seeds that would not bear fruit for generations. But they would also know that their work was necessary. Someone has to go first. Someone has to prove it is possible. Someone has to drive a stake into the ground and say, here, humanity begins again. And they would get to experience things no one in history has ever experienced. They would be the first humans to watch the sun rise on Mars, smaller and more distant than it appears from Earth. The first to see the Martian moons, Phobos and Deimos, racing across the sky in directions Earth's moon has never moved. The first to walk through canyons that dwarf anything our planet has ever produced. The first to study Martian geology firsthand. The first to truly hunt for signs of ancient life in the rocks and ice. Because Mars might have had life once. Billions of years ago, Mars was warmer and wetter. It had rivers and lakes, and likely a real ocean covering its northern lowlands. It had a thicker atmosphere, a magnetic field that protected the surface from the worst of the solar wind. Conditions that may have been suitable for life to emerge. Then, something changed. Mars lost its magnetic field, possibly because its molten core cooled and stopped churning. Without that magnetic shield, solar wind gradually stripped away the atmosphere over hundreds of millions of years. Water froze or evaporated into space. The planet became the cold, silent desert we see today. But if life did exist on ancient Mars, traces might still remain. Fossils preserved in sedimentary rocks, organic molecules locked into ice, possibly even dormant microbes still surviving in underground aquifers if any liquid water remains beneath the surface. Mars colonists would have the opportunity to search for this evidence, to answer one of the most profound questions in all of science. Did life arise independently on Mars? Or is Earth the only world in the solar system that ever hosted life? Finding evidence of past life on Mars would revolutionize biology and our entire sense of place in the universe. It would prove that life can ignite wherever conditions allow, that Earth is not unique, that the universe might be teeming with life on billions of planets around billions of stars. It would change everything. And even if Mars never had life, studying its geology and climate would teach us about planetary evolution, about how worlds change over billions of years, about what makes a planet habitable and what causes habitability to fail. This knowledge would help us understand Earth better, help us predict how our own planet might change, help us identify potentially habitable exoplanets around other stars. The science alone would justify the mission. But the deeper justification is simpler than science. We go to Mars and stay because we can. Because the alternative is to remain on Earth forever. Never expanding, never reaching, never taking the next step in our long evolutionary story. Humanity has always pushed boundaries. We've always wondered what was over the next hill, across the next ocean, on the next continent. Now we can look at the next planet and ask the same instinctive question, what's there? What can we learn? Can we live there? The answer to that last question is yes. But it requires commitment. It requires people willing to go and never return. It requires accepting that the first Mars colonists are embarking on a one-way journey. They're leaving Earth behind, trading everything familiar for a chance to be part of the greatest adventure in human history. They will not come back. They cannot come back, not because it is technically impossible, but because the resources required to bring them back could be better spent sending more colonists, more supplies, more equipment. Because every kilogram of fuel manufactured on Mars for a return journey is a kilogram unavailable for exploring Mars or building the colony's infrastructure. Because bringing people back would defeat the very purpose of the mission, which is to establish a permanent presence, not to visit and leave. And the colonists themselves would understand this, they would accept it. They would cast one last look back at Earth from their spacecraft, watch it shrink to a point of light, and then turn their attention forward to Mars, to their new home, to the future. This is why the first humans on Mars will never return. Not because of failure, not because of disaster, not because they were abandoned, but because returning was never the plan. The plan was to stay, to build, to prove that humans can live on another world, to take the first real step towards spreading our species across the solar system, and, eventually, beyond. It is a profound sacrifice and an almost unbearable opportunity. Those first colonists would surrender everything they knew on Earth, all the comforts, all the connections to friends and family, all the small daily pleasures of breathing fresh air and feeling rain and watching green leaves move in the wind. They would trade all of it for a harsh existence on a cold desert planet, where survival demands constant vigilance and where tragedy is always one equipment failure away. But they would also gain something no one else has ever held. They would be the first to live on another world, the first to call another planet home, the first to prove that humanity's future extends beyond Earth. Their names would live in history forever. Children born centuries from now, growing up in Martian cities with millions of inhabitants, would learn about the first colonists the way we learn about the Mayflower passengers or the Lewis and Clark expedition. And those future Martians, living in a thriving civilization with terraformed regions that have breathable air and liquid water, might look back at the first colonists with a mixture of admiration and quiet incomprehension. They might not fully grasp how hard it was, how much courage it required, how many sacrifices were made. The same way we sometimes forget how brutal life was for early colonists on Earth. The people who crossed oceans in wooden ships, who built settlements in wilderness, who survived winters without modern heating or medicine. But that is fine. The point is not for future generations to suffer the way early pioneers suffered. The point is for the pioneers to make things easier for everyone who comes after, to establish the first habitats that later colonists can expand, to set up the first farms that teach future farmers what works on Mars, to build the first infrastructure that later engineers can improve and extend, to make the mistakes so that future Martians don't have to pay the cost of going first. That has always been the role of pioneers. They go into the unknown. They face the danger. They solve the unsolvable problems. And they make it possible for others to follow. The first colonists on Mars will do the same. They will go knowing they are never coming back, accepting that sacrifice as the cost of making history, of becoming part of something larger than themselves. And as their spacecraft approaches Mars after 6 to 9 months of travel, as they prepare for that terrifying descent through the thin atmosphere, as they touch down on the surface and crack open the hatch for the first time, they will step out onto rust-colored soil under a pink sky, and they will plant the first footprint. They will speak the first words on Martian ground. They will look up at the small distant sun and the unfamiliar constellations and the 2 tiny moons racing overhead, and they will know they are home, not on Earth anymore, not ever going back, but home nonetheless. Because home isn't just where you're born. Home is where you build your life, where you contribute to something meaningful, where you belong to a community working toward a shared future. And for the first Mars colonists, that home will be a new world, harsh and unforgiving, but full of possibility. They will build that future one day at a time. They will expand the habitats, drill for water ice, tend the greenhouses, run experiments, map the landscape, and gradually, over years and decades, they will transform a lifeless planet into something that resembles a home. Not Earth, never Earth, but something new, something human, something that proves we can adapt to anything, survive anywhere, thrive in conditions that should kill us. And they will do all of it, knowing that behind them, millions of miles away, Earth continues spinning. Life goes on. People are born. Lives end. Civilizations rise and fall. And eventually, if we don't destroy ourselves, if we solve the problems that threaten us, more missions will launch. More colonists will make the one-way journey. The Mars population will grow from tens to hundreds to thousands to millions, And someday, perhaps centuries from now, Earth and Mars will be sister worlds. Two planets, hosting human civilization. Two homes for a species that started on a single world but refused to be confined to it. Two branches of humanity sharing a common heritage but developing along different paths. Each shaped by its environment, its challenges, its triumphs. That future starts with the first colonists, the ones who go and never return, the ones who trade Earth for Mars, the ones who become, in the most literal sense possible, aliens. Humans living on an alien world, adapting to alien conditions, possibly evolving over thousands of generations into something distinctly Martian. This is the story of why the first humans on Mars will never come back, not because they failed, not because they were trapped, but because they succeeded beyond what any previous generation of explorers ever achieved. They didn't just visit a new land, they made it their land. They claimed another planet for humanity. They proved that we can do this, that we can leave our home world, that we can survive on other worlds, that we can become a multiplanetary and eventually a multistellar species. The first footprints on Mars will never be erased. There is no wind strong enough to disturb them, no water to wash them away, no vegetation to creep over them. They will remain in the Martian dust for millions of years. A permanent testament to the moment when humanity took its first steps toward becoming something more than a single-planet species. And the people who make those footprints, who breathe filtered Martian air and drink recycled water and eat hydroponic vegetables under LED lights, who watch Earth set below the horizon knowing they will never stand on that world again, those people are heroes in the truest sense. They are giving up everything familiar, everything comfortable, everything easy, to make possible a future most of them will never live to see. That is why they will not come back. Because coming back would mean abandoning that future. And they are not the kind of people who abandon things. They are the kind of people who see something that needs to be done, something that has never been done before, something that will echo through history for as long as humans exist anywhere. And they say, yes, I will do it. I will go. I will stay. I will build something new on another world. And when those first colonists are old, when they have spent decades on Mars, when younger colonists arrive who were children when the mission launched or who weren't even born yet, those first pioneers will be able to look back on their lives and know they were part of something extraordinary. They won't regret the choice. They won't wish they had stayed on Earth. They will know they made the right decision because they will see what they built. Not just habitats and farms and equipment, but a civilization, a community, a home for humanity on another world. They will see children playing in pressurized playgrounds, learning to walk in the strange low gravity that turns every step into a small hop. They will see scientists making discoveries that finally answer questions humans have asked for centuries. Where did Mars's water go? Did life ever arise here? How do planets evolve from young hot worlds to old cold ones? What happens to human biology after generations in low gravity and high radiation? Those questions will have answers because the colonists were there to find them. They will see engineers solving problems that once seemed impossible. How do you manufacture electronics without the elaborate supply chains that exist on Earth? How do you build habitats from local materials when those materials are nothing like Earth's? How do you maintain technology in an environment that constantly tries to destroy it? The first generation will fight those battles. The second generation will refine the answers. The third generation will inherit solutions so well established that they're simply standard practice, the way things are done on Mars. They will see artists creating works that capture the unique Martian experience in ways Earthbound audiences will never fully appreciate. Paintings that capture the precise shade of pink in the Martian sky at sunset, when the blue near the sun shifts toward purple and the dust scatters light into patterns no Earth eye has ever seen. Sculptures carved from Martian rock, shaped by artists who understand how that stone breaks under low gravity. Music composed on instruments adapted to the thin, low-pressure atmosphere where sound travels differently than on Earth. Poetry written in the quiet of a Martian night, when Phobos and Deimos race across the sky and Earth is just a bright star, barely distinguishable from Venus. They will see community taking root, traditions forming, holidays celebrated, weddings held in greenhouses surrounded by the food crops keeping everyone alive, memorial services for those who have passed, their ashes scattered across the Martian surface, becoming literally part of the planet they helped tame. Each funeral a reminder that this is permanent, that these people gave their lives in the most literal sense for this project. They came to Mars and they stayed until the end, and they will know that their decision to go and never return made all of it possible. That without them, without their courage and sacrifice and willingness to leave everything behind, none of it would exist. Mars would still be an empty world, waiting for someone brave enough to make it home. They were brave enough. They went. They stayed. They built a future. The emotional weight of that knowledge would be profound. They would understand that their names would be taught to every child on Mars for as long as human civilization exists on that planet. The way we teach children on Earth about the Wright brothers, or Neil Armstrong, or Marie Curie. People who fundamentally changed the boundaries of human possibility. Before the Wright brothers, humans couldn't fly. After them, we could. Before Armstrong, humans were confined to Earth. After him, we had walked on another world. Before the first Mars colonists, humanity was a single-planet species. After them, we were multiplanetary. This shift from a single-planet species to a multiplanetary one represents one of the most significant transitions in the entire history of life on Earth. For 3.8 billion years, life existed only on this one world. Every organism that ever lived, from the simplest bacteria to the most complex animals, spent its entire existence within a few kilometers of Earth's surface. We are all descendants of a single origin of life, all branches of one family tree, all built on the same DNA structure, the same basic biochemistry, the same dependence on liquid water and organic carbon. Then humans built technology. We learned to understand the universe through mathematics and observation. We built machines that could leave Earth's surface. We sent probes to other planets, gathering data, testing hypotheses, expanding our knowledge. And eventually, we developed the capability to send ourselves to establish a permanent presence beyond our birth world. That capability changes everything. It means a catastrophe on Earth, no matter how severe, no longer guarantees extinction for our species. An asteroid impact, a supervolcano eruption, a pandemic, a nuclear war, runaway climate change, any of these could devastate Earth's biosphere and kill most or all humans on this planet. But if there are humans on Mars, if there are self-sustaining colonies on multiple worlds, then humanity as a species survives. The knowledge we have accumulated, the art we have created, the stories we have told, all of it continues. Civilization can recover, can rebuild, can eventually return to Earth if Earth becomes habitable again, or spread to still more worlds if it doesn't. This is not hypothetical risk management. Earth has been struck by extinction-level asteroids before, and will be again. 66 million years ago, an asteroid roughly 10 kilometers across slammed into what is now the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear weapons. It threw so much dust and debris into the atmosphere that sunlight was blocked for months or years. Plants couldn't photosynthesize. Food chains collapsed. The dinosaurs, who had ruled terrestrial ecosystems for 160 million years, went extinct, along with about 75% of all species on Earth. That wasn't even the worst. The Permian-Triassic extinction event, 252 million years ago, killed about 96% of all marine species and 70% of terrestrial vertebrate species. The cause is still debated. Possibly volcanic eruptions on a scale we can barely imagine, possibly an asteroid, possibly a cascade of compounding factors. Whatever the cause, Earth's biosphere came terrifyingly close to being sterilized. Life survived, just barely, and over tens of millions of years, evolution repopulated the planet with new species. But intelligence, consciousness, civilization, these are recent arrivals. Anatomically modern humans have existed for about 300,000 years. Civilization as we know it, with cities and writing and agriculture, has existed for about 10,000. We are newcomers on a planet 4.54 billion years old. We don't know whether consciousness is common in the universe. We don't know whether intelligence inevitably arises given enough time and the right conditions. We don't know whether technological civilization is a typical outcome of evolution or a strange fluke that has happened only once in the observable universe. But we do know that consciousness and intelligence and civilization exist here, now, on this planet. And we know they are fragile. vulnerable to catastrophes that care nothing for the significance of what they destroy. Becoming a multiplanetary species is insurance against that fragility. It is the civilizational equivalent of backing up critical data to multiple locations. If one location fails, the backup allows recovery. This is not cowardice. This is not giving up on Earth. It is wisdom. It is recognizing that sometimes the best way to preserve something precious is to refuse to keep all of it in one place. The first Mars colonists would understand this at a visceral level. They are the backup. They are the insurance policy. Their existence on Mars means that humanity can survive catastrophes that would otherwise erase us. They are living in uncomfortable conditions, sacrificing normal human experiences, exposing themselves to chronic health risks, precisely because they understand the stakes. They are not doing this for themselves. They are doing it for the species, for the future, for the possibility that human consciousness and civilization continue, even if Earth one day becomes uninhabitable. There is also a philosophical dimension that goes beyond mere survival. Humans have always been explorers. We originated in East Africa and spread across the entire planet, reaching every continent, adapting to every climate, from Arctic tundra to tropical rainforest to the high plateaus where the air thins. We crossed oceans in primitive boats, navigating by stars and currents and the flight patterns of birds. We climbed the highest mountains, not because there was anything useful at the summit, but because they were there, and we wanted to know what it felt like to stand on top of the world. This drive to push outward, to see what is beyond the horizon, is woven deep into human psychology. Some people are content to stay where they are, to live in familiar surroundings, to follow established patterns. Others feel a restlessness, a hunger to move, to discover, to taste new things. Both ways of being human are valid. Society needs both. We need people who maintain stability, who perfect existing systems, who build communities and raise children in safe, predictable environments. We also need people who venture into the unknown, who take the risks, who report back about what's out there and whether it's safe for others to follow. The first Mars colonists would belong to that second type. They are scouts, pioneers, the people who go first so others can follow more safely. They accept higher risks because they understand that someone has to, and they are willing to be that someone. This isn't recklessness. It isn't a death wish. It is courage informed by clear-eyed assessment of danger. They know the risks. They choose to proceed anyway because they value the goal more than they fear the cost. Throughout history, we have celebrated these people. We built monuments to explorers and pioneers. We tell their stories to children, holding them up as examples of human capability at its very best. The first Mars colonists would deserve similar recognition, not because they went to Mars, but because they stayed, they committed. They built something permanent. They turned an abstract human capability into concrete reality. Before them, we could speak theoretically about living on other planets. After them, we actually do it. Their decision to never return would be central to their legacy. They could have demanded a return option. They could have insisted on ascent vehicles and fuel plants and the entire support architecture needed to bring them back. But they recognized that insisting on those return options would have made the mission exponentially more expensive and difficult, possibly impossible with current technology and budgets. So they accepted a one-way trip. They surrendered Earth forever. They made the ultimate sacrifice, not of their lives immediately, but of their ability to ever return to the world where they were born. That sacrifice enables the mission to happen at all. It reduces costs, simplifies logistics, allows resources to be focused on making the Mars colony sustainable rather than on bringing people back. Every kilogram not spent on ascent vehicle fuel is a kilogram that can be spent on greenhouses, tools, scientific instruments, medical supplies, things that improve life on Mars and enable the colony to grow. And growth is essential. A colony of 4 to 6 people is a foothold, not a civilization. It is vulnerable to accidents, to equipment failures, to plain bad luck. If 2 people die in an accident, the colony might not have enough people left to maintain all the critical systems. But a colony of 40 has redundancy. A colony of 400 has specialization, with doctors and engineers and farmers and teachers. A colony of 4,000 has culture, economy, political structure. It becomes self-sustaining, not just technologically, but socially and psychologically. Getting from 6 to 6,000 requires continued missions from Earth, at least in the early decades. Each mission delivers more colonists, more equipment, more genetic diversity, more knowledge and skills. The growth might be exponential if each successful mission encourages more funding and more volunteers. Or it might be linear, with missions arriving every couple of years as budgets allow. Or it might stall if missions fail, if public interest fades, if political priorities shift. History offers examples of all three patterns. European colonization of the Americas started slowly, with several outright failures, then exploded as success became visible and economic opportunities attracted massive investment. Antarctic research stations grew slowly and stayed small because there was no real economic incentive to support larger populations. Space station programs have shown that sustained presence in a hostile environment is possible, but politically fragile, dependent on continued funding and international cooperation that can evaporate with changing governments. Mars colonization would likely follow a boom-and-bust pattern. Initial excitement and rapid growth as the first missions succeed and capture public imagination. Then a plateau as the challenges become apparent and costs mount. Possibly a collapse if a major disaster kills colonists or if economic recession on Earth forces budget cuts. Then gradual recovery as new technologies reduce costs or new motivations emerge. The overall trend would be upward, but with setbacks and difficult periods that test the commitment of everyone involved. The first colonists would experience the initial excitement, but might not live to see the full realization of the colony they founded. They'd be in their 40s or 50s when they landed, after years of training and selection. They would spend perhaps 20 to 30 years on Mars, working to build the colony, welcoming new arrivals, passing on their hard-won expertise. Then they would age, their bodies wearing out faster than they would have on Earth due to radiation and low-gravity effects. They would reach the end of their lives on Mars, probably in their 70s or 80s, surrounded by a small but steadily growing community. Their funerals would be community events. Everyone on Mars would attend. They would gather in the largest pressurized space available, share stories about the deceased, celebrate their contributions, grieve their loss. Then they would carry the body outside in a slow, careful procession, suits moving at low-gravity tempo, and commit it to the Martian soil. No traditional burial, because the permafrost makes deep digging extraordinarily difficult. More likely, the body would be placed in a designated area, covered with rocks, marked with a simple monument. The first Martian cemetery, where the founders of human civilization on Mars rest permanently. Future colonists, arriving years or decades later, would visit that cemetery as a kind of pilgrimage. They would stand before the markers of the first colonists and reflect on the courage it took to come here, knowing they would never leave. Children born on Mars would learn about these people in school, study their decisions, understand that their own existence is possible only because these pioneers accepted a one-way ticket. And somewhere among those later arrivals, there might be the children or grandchildren of the first colonists. Children who were small when their parent left for Mars, or who weren't even born yet. Who grew up on Earth listening to stories about a mother or father or aunt or uncle who went to another planet. Who saw video of the landing. Messages sent back across the void. Images of the red landscape. And who decided they wanted to see that world themselves. To follow their family member's path. To be part of the same grand endeavor. These second-generation Mars migrants would arrive to find a world their relative helped create. They would walk through habitats their family member built. They would eat food grown in greenhouses their family member designed. They would meet people who worked alongside their family member who could share stories and memories. And if they were fortunate, if the timing aligned, they might arrive while their family member was still alive, still lucid enough to recognize them, still able to understand that this person from Earth had crossed the Gulf for a final reunion. Imagine that meeting. An elderly colonist, body bent by decades of low gravity and radiation, mind perhaps a little clouded by age but still working, seeing for the first time in 30 years someone from their old life. Their daughter, herself now middle-aged, who made the 6 to 9 month journey to Mars knowing her parent might not survive long enough for her to arrive. They would embrace as well as spacesuits allow. Or, if they were inside the habitat, properly without the encumbrance of suits. They would talk for hours, for days, bridging decades of separation in long, halting conversations. The colonists would share what they had learned about Mars, about building something new, about the strange satisfaction of seeing a dream become reality. The daughter would share news from Earth, updates about family and friends, changes in technology and culture that the colonists had only heard about through messages and reports. And then, eventually, the elderly colonist would reach the end. But in their final days, they would know their family had come, that the connection had not been completely severed. That love can bridge the distance between planets, even if it takes 30 years to complete the journey. They would spend their final days on Mars, the planet they chose, surrounded by the community they helped create, with family present for the end. Not a bad way to go, all things considered. Better than many people are given on Earth. These stories would become part of Martian culture. The family that spans 2 planets, the pioneer who never returned to Earth, but whose children eventually came to Mars. The sacrifice and the reunion. The permanent separation and the unexpected connection. These narratives would help future Martians understand their history, their relationship to Earth, the choices that brought them into existence. Because everyone on Mars is there because someone made a choice. Either they chose to come themselves, or their parents chose to come, bringing them as children or conceiving them after arrival. No one on Mars is there by default. No one was born into Martian life without some act of will somewhere in their family history. This would create a culture fundamentally different from Earth, where most people live in the country they were born in, following patterns established by accident rather than choice. Martians would grow up understanding that their existence required someone's active decision. That humans are not on Mars by accident or evolutionary inevitability, but because specific people made specific choices to go and to stay and to build. This awareness might foster a culture that values intentionality, that sees life as something you actively create, rather than something that happens to you. Or it might create a kind of pressure to justify one's existence, to prove that you're worthy of the sacrifices your ancestors made. Or it might produce a combination of both, a culture simultaneously empowered and burdened by the weight of its own origin story. Earth cultures developed over thousands of years, shaped by geography, climate, available resources, migrations, conquests, trade, technological change, and countless other factors. Martian culture would develop much faster, condensed into decades or centuries, and shaped primarily by the constraints of living on a hostile planet and the shared experience of being pioneers. The first colonists would set the tone, establish the early norms, create the founding myths. Later arrivals would modify and extend that foundation. Children born on Mars would absorb it and make it their own, changing it further. Within a few generations, Martian culture would diverge significantly from Earth culture. Language would shift, developing Martian-specific vocabulary and possibly new grammatical structures. Social norms would adapt to the realities of life in confined spaces with limited resources. Values would shift to emphasize cooperation, sustainability, and long-term thinking, because individual survival depends utterly on community survival. The artistic and intellectual traditions would reflect the Martian experience, creating works that Earth audiences might find alien or incomprehensible, even though both societies share common ancestry. And the first colonists, those who made the one-way trip, would become mythologized. Their real struggles and failures and human flaws would be smoothed over, replaced with idealized versions that serve the needs of later societies. They'd become cultural heroes, larger-than-life figures who embody virtues that Martian society wants to promote. The truth of who they actually were, ordinary humans with extraordinary courage who made an irreversible choice and lived with the consequences, might get buried under the legend. But that's how cultures work. We tell stories about our origins that serve our present needs. The stories don't have to be perfectly accurate to be meaningful. What matters is that they convey important truths, that they help people understand where they come from and why they exist. The first Mars colonists, by choosing never to return, would give future Martians a powerful origin story. The pioneers who left Earth forever to build a new world, who sacrificed everything familiar for the idea that something better could be created elsewhere, who bet their lives that humans could thrive on Mars and prove themselves right. That story would inspire generations. It would be told to children learning their history, referenced in political speeches when leaders need to evoke shared purpose, remembered in quiet moments when someone faces a difficult choice and needs courage. The story of the first colonists who didn't come back because they never intended to. Because coming back was never the plan. The plan was to stay, to build, to transform Mars from an empty world into a home. And in executing that plan, in living that story, they would do something no other humans have ever done. They would prove that our species can persist beyond our birth world, that we are capable of adapting to conditions radically different from what we evolved for, that human consciousness and civilization are not confined to Earth, but can spread, can take root in new places, can establish themselves permanently on multiple worlds. That is not just exploration, that is not just adventure, that is existential insurance for the species. That is taking evolution into our own hands and directing it towards survival across cosmic timescales. That is ensuring that whatever happens to Earth, whether catastrophe, gradual decline, or simply the natural evolution of our star toward its red giant phase billions of years from now, humanity continues somewhere. Our ideas, our art, our knowledge, our consciousness, all the things that make us human, persist and grow and change and eventually become something we can't predict or imagine. Thank you for joining me on this exploration of why the first Mars colonists will embark on a one-way journey. If you found this thought-provoking, a like or subscribe would help us continue examining the profound questions about humanity's future in space. These deep dives into what space exploration really means take considerable thought and research to create properly. The journey to Mars represents more than just technological achievement. It represents a fundamental shift in how we think about ourselves as a species. We are no longer bound to one world. We have the knowledge and the capability to spread across the solar system. Whether we choose to do so, whether we commit the resources and accept the sacrifices, remains to be seen. But if we do, if those first missions launch and those first colonists land and stay and build, they will be doing something no generation before them could do. They will be making humanity a multi-planetary species. They will be securing our long-term survival. They will be opening a frontier that could keep us exploring and discovering and growing for thousands or millions of years. And it all starts with people willing to go on a one-way trip, willing to leave Earth forever for a chance to be part of that future. That is not just exploration. That is transformation. That is evolution. That is humanity taking the next step. And those first footprints on Mars, the ones that will never fade, will mark the moment when we took that step, when we proved we could, when we chose to reach for something greater than ourselves. That is why they won't come back. Because they are building something that will last far longer than any individual life, something that will outlive nations and civilizations, something that will endure as long as humans exist anywhere in the universe. They won't come back because they are going home, to a new home, to Mars. And that is exactly where they will stay.